So today I'm going to start a section I'm going to take up actually the rest of this week, which is the last week of this term. And then when we start the next term, it will take me another week's worth of lectures as well to discuss on one aspect of other. But I want to talk about energy momentum, specifically the energy momentum tensor. What we're going to see is that it's central conserved quantity in a conformal field here. So to that end, I need to define what the energy momentum tensor is, and I will talk to you about the fact that it's not unique, but then neither is anything else start with another zero. It's not. And then we're going to talk about how you would accommodate certain deficiencies of canonical energy momentum tensor by modifying one computation. It's called the quantity tensor, which you would encounter in UGR. I'll tell you why we want to modify the energy momentum tensor in particular, how it's gravity. We'll see it in the context of GR, and that will lead us to another definition of the energy momentum tensor. And then I'll try to restart with the definition of the next lecture. And then when we come back in the next term, we will talk about when things go wrong, otherwise known as anomalies. And I will tell you about the formal anomaly and two very important theorems that are very contemporary. One of them was proved only a couple of years ago called the A theorem, and then there's the C theorem. And both of these things are very important in the context of understanding the structure of what we do. Okay. But they're all kind of hinged on this idea of the energy momentum test. So what we've learned so far is that Tensor theorem is a constructive proof of the statement that to every continuous global fluidity there exists some conserved charge. Not only does Tensor theorem tell us that there exists such a charge, tell us how to construct a charge. If you're mathematically inclined and I present you a theorem, typically you want to know about two things, not only existence but also uniqueness. Is the energy is the conserved current that you construct from notice theorem unique? So the question today is the current unique? Yeah, you kind of hope that it is. I give you some symmetry. You construct the quantity that's a charge associated with that symmetry. Yeah, we hope that the charge you construct is unique. That the charge you construct, the charge you construct are not two different charges, depending on two different aspects of physics. But to clarify this, we need to clarify what it means by the aspect of physics. So the answer to that question is decidedly no, it is not unique. Okay. So let me show you why it's not. So to see this, suppose I add to the conserved current J mu. So suppose J mu is a conserved current. But what that means is that its divergence vanishes, so d mu J mu is 0. But what I'm going to do is add to this thing another quantity. That quantity I'm going to call V mu nu. And I'm going to assume that V mu nu is antisymmetric. So V mu nu is some antisymmetric tensor. I can build this antisymmetric tensor out of the field of the theory and then just written in some way. I don't really care how I build it. I don't really care what it is. All I really care about is this antisymmetric tensor. Okay. So I have some fields in my theory, and I use those fields and their derivatives, and I build this antisymmetric object, even nu. Don't care what it is. So now what I'm going to do is I'm going to construct an improved current. To define the terminology there will be explained, which is possibly construct specific currents. So we're going to define an improved current. Let's say J nu tilde as J nu plus the derivative of E union. Okay, so we do a quick sanity check on the indices line up nicely. I'm using the left hand side, I'm using the right hand side, and then we're free next to this thing. That's some of the news. Okay. My claim is that this new current has the following properties known. One is that it is also conserved. The new tilde is conserved. It's also conserved. That is to say, the conservation properties of J will not spoiled by adding to this guy because the new J tilde is the new J mu plus the mu the new v mu mu, and this guy vanishes because J mu is conserved. And this guy vanishes because it's contraction of a symmetric object, because I can interchange these two derivatives with an anti-symmetric object. So this is necessarily zero. Second property to note is that J mu tilde leads to the same conserved charge. But this is because the charge that I construct J nu tilde, let's call it Q tilde. Q tilde is the integral in the space of the time component of this guy, which is the integral dvx of the time component of J naught plus d nu v nu naught but in the sum there's no d naught v naught because v naught is zero because v is an antisymmetric object, so this is just spatial derivatives. This breaks up into two things. The first one, the integral of J naught over dvx over the spatial volume, that's just what we're calling the charge. The second part is the integral over space of vi, no, but this is just a total derivative. So Q tilde, charge associated to J tilde, is the same as Q, charge associated to the upshot of this is that I can always add such an object to the Nernst current that I construct to produce another Nernst current that has slightly different properties. among the properties that they share is that they are both observed and they both be the same charge. Okay, so I'm guaranteed that the charge that I measure from this modification of the elliptic current is the same as the charge that I measure in the elliptic current. So when I said, you construct another current, you construct an elliptic current. Well, the thing that you're going to be measuring is the charge, and that charge will come out the same. Physical aspects of the theory are these some of the physical aspects are going to be the same. We're going to see that they're not all the same. Okay, so I'd like you to keep that statement in mind. The current that you construct is not unique, and it can be modified, and in some cases it must be modified. Okay, so now I want to consider a theory that's invariant under space-time translation. I want to ask, what is the associated current? So consider a theory. We'll do some examples of this. Invariant under space-time translations. X mu going to x mu minus a mu. A mu is just some constant vector. So, in order to work out the associated charge, what we do is follow the mimic what we did previously, promote this that something is dependent on the x mu, and then we construct delta s, and we require the delta s match. So the associated delta s that comes out of this is the integral x. Okay. So if you remember what we did in the case where we had some parameter here and it was a scalar parameter, we had this thing proportional to, it had to be first order in the parameter, and had to be the derivative of that parameter, right? For the reason that I illustrated last time. So the point here is that this guy now carries a Lorentz index. But all the previous arguments that we gave about it being linear and a mu, depending on the derivative of a mu, still hold for exactly those reasons, right? So now I'm going to find that when I write down delta s, there's going to be something that's proportional to the derivative of this a mu. Okay. So here I'm going to have something that is going to look like d, let's say mu a mu. The constant of proportionality needs to be something that makes sure that this guy here, because this guy is a Lorentz scalar, that what's sitting in here must be a Lorentz scalar. It has to carry two Lorentz indices as well. So it's going to be a rank 2 tensor. That rank 2 tensor we'll call T mu. Okay, so just following the arguments that we had previously, this has to be the structure of delta S. Okay, can't be any other way. So basically, the statement is, as my parameter, as I increase the rank of the parameter, parameterizing symmetry, so too must the observed charge rank increase. We had a vector being conserved the last time, a tensor being conserved in this case. So this tensor is conserved, and to show that we integrate by parts. So integrating by parts and assuming that everything moves upon the boundary, we find that setting S 0 gives conservation law d mu t d mu t mu This object here, it's called the energy momentum or depending on the literature you're looking at, stress energy. Yes. And this statement is nothing but conservation of energy and momentum. It's pretty cool how it comes out of simple arguments that we've been making previously. Right? We did all the heavy lifting in the previous couple of lectures, and now it pops out that in a system that is invariant under space-time translation, energy and momentum are. And in fact, we can separate out the translations into the translation in time and translations in space, and we can find the translation in time corresponds to energy, translation in space corresponds to energy corresponds to calculation of energy and momentum. Okay, so this is one of the really kind of beautiful aspects of this theorem that just pulls out all this stuff that we've done piecemeal since first year. Honestly, roughly since my kindergarten, and pulls it all together in this really neat way that you can see, all tied together. Okay, so good. We've established that a theory that is invariant over space-time translations, the conserved quantity is energy and momentum. Right? It's a tensor, and I can construct an unusual vector current out of this by tracking it into something. We'll talk about that in a little bit. But the associated conserved current law is nothing but conservation of energy and momentum. So let's do an example then to illustrate how it works. And in particular, I've given you this formal argument as to what the energy momentum tensor is. There's a coefficient in front of the d mu and u term that comes from basically arguing that this is the way things are. That's the only way we can. Yeah. But I can give you a construction that allows you to actually compute the energy momentum tensor given a particular data. So let's see how that works. So the example I want to use in this case is to work out the energy momentum tensor for a scalar field with some Lagrangian that doesn't manifestly depend on x mu. Okay. So consider a theory with Lagrangian empty L function of, let's say, phi and d mu phi. Okay, so there's no manifest dependence within x coordinate as you. That's an important point. No explicit x. So let's do what we just did above and take space-time translations. So under space-time translations, where x mu goes to x mu minus some mu, the following happens to the fields. Phi of x goes to phi of x plus a. So if we make an expansion of this phi of x plus a, this means that the change in phi, delta phi, is just a mu d mu phi. This is just by theory. Okay. Similarly, the change in d mu phi mu phi. It is a mu d mu of d mu phi. So what does it mean? There's no explicit dependence on x, the Lagrangian. So a change in the Lagrangian is an induced change by the fact that because phi depends on x, if I make a change in x, phi changes, that's why I have this delta phi, and so does its derivative, that's why I have this delta dv phi. And those changes induce a change in delta x, in L. But it follows that change induced in the Lagrangian is just dl by phi delta phi plus dl by d mu phi delta d mu phi. And now we substitute in for each of these. So this is dl by d phi a mu d mu plus dl by d mu phi a mu d mu phi. I can take out a mu from here. This is just a mu times dl by d phi d mu phi plus dl by d mu phi d mu phi. But this whole thing here in brackets is just what we would call delta L. Sorry. What we would call d mu. In other words, since L has no explicit x dependence, it only changes because phi and its derivative change. So what have we discovered? We've discovered that delta L can be written as d mu of some tensor, some vector k mu. If we identify the vector k mu with a mu times the Lagrangian. Remember, that's what we were trying to do when we construct delta currents. So from here, we can construct the delta current. J mu. And J mu was just dl by d mu phi minus this k mu guy. Once we identify what the k mu is. So substituting back in, this is the dl by d mu phi. That is a mu d nu phi minus k is a nu times the Lagrange. So this is just a nu downstairs, times something has two Lorentz indices, a nu downstairs and a nu upstairs, TBD, where I define this guy now to be what's remaining behind once I pull out this overall A. Yeah, T in nu is what I'm calling dl by d nu phi u phi minus eta in nu okay. There are a couple of things to note here. One is, if you go and look up what the energy momentum tensor looks like, let's start with the Lagrange, and this is the expression that we find. So given the Lagrange density, I take the derivative with respect to the derivatives, multiplied by the derivative, minus eta mu times the Lagrange itself, and that's the energy momentum tensor. So a couple things to note. One is this sign here is dependent on the metric curve. So we're working primarily with minus signs in the diagonal metric. This minus sign comes again. This will change. The plus sign in the mostly plus metric. That's important. The other point to note here is that this is consistent with what you understand of the definition of the Hamiltonian. So to see that, let's make the following observation. If I choose mu and mu equal to 0, then I'll find that T naught naught is dl by d phi dot. But dl by d phi dot is what you were calling the momentum, canonical momentum, or phi. D naught of phi is the time derivative of phi. Phi dot. And then minus the Lagrangian. This is like px dot minus the Lagrangian. It's what you would call the Hamiltonian is. It's the Hamiltonian. Density. Here. Talk about the usual name of the John. Also name. Okay. So the time component of the energy momentum tensor is nothing but the energy density. Hamiltonian density. If I integrate this guy over space, then I get the Hamiltonian for the energy. Yeah, the question was the K right. The K changes is basically equal to A. How do we change to the new? I think if you pull out I need to pull out.
I think that the index is wrong. It's AU now, not H.
Yes, sorry, you're right. Is that right? Yeah. Okay, yeah. Yeah, I need to pull out a new and then make new into a new, that's why I have it. Okay. The problem with this energy momentum tensor, otherwise known as the canonical energy momentum tensor, that this is the canonical energy momentum tensor. The problem with canonical energy momentum tensor is that it's not entirely satisfactory for a number of reasons. One reason you will discover for yourself when you mimic this construction and calculate the canonical energy momentum tensor for the electromagnetic field, back to electrodynamics and in the next tutorial. And that is, if I calculate TB nu, this canonical wave for the electromagnetic field, it is not gauging variance. Now, the energy momentum tensor contains information about the electromagnetic field. These are the observable theory. Right? All your physical quantities have to be gauging variant. They should not depend on how you choose to describe the physics. Physics is physics. Right? So physical quantities need to be gauging variant. If you calculate this, the canonical energy momentum tensor for the electromagnetic field, it is not gauging variant. This keeping here for the electromagnetic field is not gauging variant. So cannot encode physical energy and momentum. Yes, that's the problem, right? Because I'm trying to use the energy momentum tensor to encode the physical energy and momentum densities of the system as I put it in E squared minus E squared. And the energy momentum tensor that is canonically generated by this theorem does not do that because it is not getting variant. That's one problem. Second problem is that it's not symmetric. Right? This is certainly symmetric, but this is not. So the canonical energy momentum tensor so you might say, well, okay, what do I really care that this thing is symmetric or not? I give a construction from this theorem, tells me you have a conserved quantity, you have symmetry, here's the conserved quantity. It doesn't have to be symmetric. So why is it a problem that this thing is not symmetric. Well, here's why it has to be. So it being not being symmetric is not a problem all the time, but it is a problem if I think about physics on a more broader scale. So we call the Einstein field equations. These equations say the following: omni minus a half v mu are let's add one of the constants, the plus lambda v mu equal to 8 pi constant divided by c to the 4. T check it out. T the direct appearance in Einstein field equations of gravity. Right. The content, physical content of this equation. 3. Physical content of this equation is that energy and momentum gravitate. Anywhere I have energy and momentum, even for massless particles that carry some energy, so they don't get to light, they gravitate. Right? So the statement here is that energy and momentum gravitate. But the left-hand side, so this guy here is called the. How many of you have not worked with the energy with the outside field? No? Okay. So this guy on the left-hand side is called the Ricci tensor. One of its key properties is that it's a rank 2 symmetric tensor. This is the metric. And it is a rank 2 symmetric tensor. This is the cosmological constant. And this is constant, so it doesn't change the tensorial property of the thing is multiplying. This is a scalar called the Ricci scalar. Means that this term here is a rank 2 symmetric tensor. So rank 2 symmetric tensor, symmetric tensor, symmetric tensor, all added up, the tensor properties, the thing on the left-hand side is a symmetric tensor, which means that for the thing to be true, the thing on the right-hand side has to be a symmetric tensor. So the statement is that if I want to this statement, Einstein's theory of relativity to be true, then the energy momentum tensor has to be symmetric as well. So I can't couple an energy momentum tensor that is not symmetric to gravity. That's the outcome. Okay. But there's something else that we can get from this Einstein field equations. Namely, that the Einstein field equations are the equations of motion for the gravitational field. They're the equation of motion in the same sense that you get the Gordon equation as the equation of motion for scalar field. Right? You start off with an action, you demand that the action is stationary under variations of your dynamical variable, and out pops the equation of motion. So in fact, this equation B, the outside field equation, gives us another definition of the energy momentum density. Namely, that the right-hand side of that equation B implies that the energy momentum tensor is, and I'm taking this as a definition, what? 2 over the square root of the determinant of the metric times the functional derivative of the Einstein-Hilbert action, which is the action that encodes the dynamics of the gravitational field, with respect to the dynamical variable in the problem, which is the metric field. And this energy momentum tensor is manifestly symmetric because the right hand side is symmetric. So this thing is gauge invariant and manifestly symmetric. Okay. The gauge invariance here is not the same gauge invariance that I complained about in the electromagnetic case. In the electromagnetic case, the gauge invariance is gauge invariance under the U1 transformation of the electromagnetic field. The gauge symmetry enjoyed by gravity is significantly larger. It's the different. It's a factor. You can make changes of variables, and it doesn't affect the gravitation. Okay. So when I say gauge invariant in this case, I mean gauge invariant under the different models. So the problem we have is that in general, this TU and this TU do not agree with each other. And if they don't agree with each other, they're actually encoding different things. It's our job to figure out the physical system in question. So, in general, TU from 3 and 4 will not agree. However, what we've learned is that we can always modify or improve the canonical energy momentum tensor to make them again. One such modification is called Belafonte tensor. The Belafonte tensor or Belafonte Rosenfeld tensor is constructed from the energy momentum tensor, the canonical energy momentum tensor. So this is what was kind TBD, the frontage. And it is TBD, the canonical language momentum tensor plus 1/2 following derivative. The lambda of S mu lambda plus S mu lambda minus F lambda mu. What is the scatter object? S here is called the spin current. Spin current is physically a reflection of the fact that in relativistic field theories, particles can carry energy and momentum not only due to their motion, but also due to their angular momentum that is due to their intrinsic spin. Right? And this term here encodes and accounts for the fact that the angular momentum could also depend on the spin of the particles. Okay. And the Bellatron tensor, this is my example, the Bellatron tensor is a sum of those three energy momentum and the bound energy momentum. So to finish today, I want to just cycle back to our discussion of the energy momentum tensor and what, if any, constraints are imposed on the energy momentum tensor by things like having a couple of gravities. Okay. So suppose first that the confirmation I make on X mu is an isomorphic method. So it's something that leaves some confirmation that leaves a method invariant. So suppose that X mu to X mu plus psi mu is an isometry of metric. Recall that what this means is that this vector here must be a vector. Okay. And this vector means that it needs to satisfy the Kelly vector. And my claim is that current that I construct from T nu by contracting it with the vector field is conserved. So this construct the following current. This is an index. The label. This guy that I get by contracting TBD with signing. It's why is this? Well, if I calculate d mu of j mu. And this is d mu of t mu nu contracted with sine u plus t mu d mu sine u. This guy's zero because I know that t mu is conserved. Maybe we mentioned tensor. And this guy is 1/2 of t mu nu d mu plus d mu by mu if t mu is symmetric. Right? So if it's symmetric, what I do is I divide by half and multiply by 2. Take each one of these guys, exchange the labeling of the indices, use the fact that it's symmetric, put the index around, pull out the TVU, there's a factor of half. Then I have this side. But this side is here. Because the side I'm doing right now. Now I can turn the argument around and say that if side K vector, that this guy is conserved if and only if T mu is symmetric. Here's another reason to require that the energy momentum density is symmetric. But we can go a little bit further. And ask, what if we're dealing with a not with any other homology, but a conformal solution? What if sine u to sine u plus x mu to x mu plus sine u is a conformal solution, then sine u is a conformal thing. What this means is that it's a conformal thing. So d mu sine u plus d mu sine u, it's 2 over d dimensions d dot sine eta mu. Well, what this necessarily means is that the conserved current, the side that I construct in the same way, is conserved. The d mu, the current is conserved. 0, following exactly the same argument. Except now, it will rely on the fact that eta mu nu t mu nu, otherwise known as the trace mu vanished. In other words, in a conformal field theory, in a theory that is invariant of a conformal transformation, the energy momentum tensor will not only be symmetric, it must also be traceable. CFTs require that the trace of the energy momentum tensor vanish. Okay. So let me leave it here. Then on Friday, we'll pick this up and I will instruct, I will do a particular example of CFT. In which the energy momentum does not vanish, and then we'll go how to prove it to, sorry, the energy momentum does not vanish, and then we'll show how to prove it by adding this little improvement tab, and that theory does not work whether it's called theory. Okay.